Okay, so before we continue, let's just review some basic matrix notation. So a matrix obviously consists of a set of elements that can be represented by a single syllable. So for example, the matrix A, which we represent with square brackets around it, is composed of a set of elements in the following manner. Where every element, so ij, is the individual element of this array, of this matrix. And we say that this matrix has n rows and m columns, and that the dimension of this matrix is the number of rows multiplied by the number of columns. And if n equals m, then we can say that the matrix is square. Okay. So carrying on this discussion, the diagonal of our matrix, this set of elements here, is called the main diagonal or the principal diagonal of the matrix. All right, now let's go through some special matrices. Okay, we say that a matrix is symmetric if each one of its elements, aij, equals the elements in the jth row and ith column. So in real terms, this may look like this. Here we have a matrix consisting of values that are symmetric across the diagonal. So here we have our diagonal, and we can see that the values are symmetric across this diagonal. Okay, now a diagonal matrix is a square matrix where all the elements of the main diagonal are equal to 0. So for example, if we had our matrix A equal to this, so we have a diagonal consisting of an element A11 and A22 with zeros on either side of that diagonal. We say that it is a diagonal matrix. And the identity matrix is termed I, and it consists of elements equal to 1 along its center diagonal, and everywhere else being 0. Okay, so an upper triangular matrix is one in which all the elements below the main diagonal are equal to 0. And vice versa, if we have a lower triangle, all the elements above the center diagonal will be equal to 0. Okay, and a banded matrix, let's just add a few more terms here. Banded matrix is one that has all elements equal to 0 with the exception of a band centered around the main diagonal. So we could have terms A12, sorry, A11, A12, A21, A22, A23, A33, and A32. Okay, let's clear this up. And let's go on to talk about some of the matrix rules. Okay, so a matrix, two matrices, let's say we have two matrices A and B, they are only equal if every single element in A equals the element in B. We can add these two elements, these two matrices, so A can be added to B to get a new matrix C, where each element in C, so Cij, equals the sum of each element in A plus B. And this is the same for subtraction, except this becomes a minus. Okay, now both subtraction and addition are commutative. So that means that the A plus B equals B plus A. And they're also associative. That is that A plus B plus C equals A plus B plus C. Okay, now this leads us on to the next very important point, which is multiplication. So let's just clear this. Now, multiplication, if we multiply a matrix by a scalar, we just multiply every element in that matrix by the scalar value. What's really important is how we multiply two matrices together. So we could, if we multiply A and B, so A multiplied by B, we obviously create a new matrix. We can call this C, all right? And this is an important distinction where every element in C, Cij, is equal to the sum from k equal to 1 to n of aik bkj. Now let's just look at this in a little bit more detail. What we are saying here is that element ij, so let's say ij is equal to, I is equal to 1 and j is equal to 1. So C of 1, 1 equals the sum, k equals to 1 to n, we have n terms in our matrices, of a1 k multiplied by bk1. So in other words, can you see that we are taking the row of A and multiplying it by the column of B? So if we had A with these elements, A11, A12, dot, 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 and we had B with these elements, B11, B21, B31, we would multiply each one of these terms, A11 multiplied by B11, A11 plus, sorry, A12 multiplied by B12. And that would form the new element in C on the first row and first column. Okay, now there are some important rules about multiplication, and that is if the dimensions of A and B are suitable, multiplication is associative. That is the multiplication of A, and I'm going to drop my square brackets, AB multiplied by C is also equal to A multiplied by B times C. And it is also distributive, so A multiplied by B plus C is equal to AB plus BC. But something that's very important is that AB does not generally mean, is not the same as BA. Okay, so let's just get on to division quickly. Now division is actually not a defined operation when we talk about matrices, and but we can talk about the inversion or the inverse of a matrix. So if an inverse of a matrix exists and that matrix is square and non-singular, then the inverse, so multiplied by the matrix A, which is obviously also equal to A multiplied by A inverse, that equals to the identity matrix. Okay. And the transpose of A, so A transposed, is equal to the following. So if we have a matrix A with the following elements, A11, A12, A21, dot, 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 then the transpose of A is equal to A11, A21, A12. So what I've done here in this transpose is I've swapped the elements around. So what was a row is now a column, and a column is now a row. And this happens across the diagonal. And then one final thing, we are going to go through how to represent linear algebra, the set of linear algebraic equations in matrix form. So if you recall right at the beginning of this discussion in our first video, we had a set of linear equations that looked something like this, with constant terms A11 multiplied by x1, and this was going to A1n multiplied by xn equal to b1, and we said that was equal to an1 multiplied by x1 and an multiplied by xn equals to bn. So in matrix form, we can rewrite this as the matrix A multiplied by some column vector x equaling another vector b. Okay, where each element in A, so A is made up of A11 all the way to A1n and so on and so forth down to ANN. This is a square matrix because the number of rows equals the number of columns. Okay, now the formal solution to our above formulation is to say that the inverse of A multiplied through, again I'm just dropping the square brackets, equals A inverse multiplied by B, and because our this term on the left here, A inverse multiplied by A, is equal to the identity matrix, which is 1, then we can rewrite this as x equal to A inverse multiplied by our column vector B. But something that's really important is that this is not the most efficient way of solving a linear algebraic equation.